partial of f with respect to x, partial of f with respect to y, partial of f with respect to z, right? Whatever our scalar function is, the partials with respect to x, y, and z, those partials should match up with the component functions of the field. So this should be partial f with respect to x, this should be partial f with respect to y, this should be partial f with respect to z. And so I'm going to start with one of them and start building backwards like I did in the previous example. Yep.
Does it matter which one we start with?
It does not matter. I always start with x because it's, you know, the first one from left to right. But you could start in the middle with the partial f with respect to y or z. You could look at them, see what's easier to you. All right, so I'm going to start here. We know that the partial of f with respect to x must be 2xz plus y squared. All right, that's what we know. I'm now going to integrate that with respect to x to figure out what little f is. So we do the integral with respect to x, integral with respect to x, right? That's what I'm going to do. On the left side, we get little f. On the right side, we're going with respect to x. So z is a constant here. We should just get x squared z plus x y squared or y squared x, however you want to write that. Right? Plus it could have y's in it or z's. So I'm going to say, do you want to use g again?
Yes.
Yes? I would write g, but I say g of y or z. It's a function of g. The g function could have y's or z's in it. Because if you differentiate this with respect to x, if no x's are here, then that's going to 0, right? So this cannot have x's in it. Yeah? Just keep playing this game. But when I now take that and differentiate with respect to y, right? Let's differentiate this with respect to y now. This will be 0. This will be 2xy, right? 0, 2xy. And then what's derivative of that with respect to y? No idea, right? No idea. But I'm going to put g sub y. So that's the partial of g with respect to y. But that has to be equal to what we see up here, right? Those two have to match. But that implies that 2xy plus partial g with respect to y must equal 2xy. That's coming from here, right? And this side of the equation, right? This side of the equation is coming from our work. So the work that we've done has built up what this is, but we need it to match we need it to match with what's up there. And that tells you what g sub y should, or partial g with respect to y should be 0 then, right? This seems like the game we just played a minute ago. Didn't we have the same result? Okay, and when we integrate this, we do not get a constant this time. Because g could have z's in it still, right? We know it doesn't have we know it doesn't have y's, but it could have z's still. So when I integrate now on both sides with respect to y, my left side is g, and my right side is what? Something that has z's in it potentially. I can't use g again. H. I'm going to use h. G has to be some function of z, h of z. The antiderivative of that's g. The antiderivative of this is potentially some function with z's. Yeah? Well, now we go back to this. Remember, this is where we were, and we were like, okay, we have f kind of. We're off by that much, right? But now I can tell you a little bit more about this. What can I tell you about this? It has to have just z's in it. So I can go to that now and say, so f now, I'm narrowing what f can be, narrowing down what f can actually be. Some function of z is the only thing possible out here now. And now we're going to play this game one more time. I'm going to take the partial of that with respect to z and make it match with what's here. And this will be my last time through. So that's that. And then we take the partial of f with respect to z. Here we'll get what? X squared plus, yeah, whatever derivative h is with respect to z. Again, we don't know what that is. That could be anything. It just can only have z's in it, and maybe some numbers, constants. So this, though, has to match that, doesn't it? So that implies that x squared plus some derivative, partial derivative h with respect to z, has to be what's up there, which is x squared plus 3z squared. And if you subtract x squared on both sides, you get partial of h with respect to z is 3z squared. I'm almost there. What next?
Integrate that.
Integrate with respect to z. Okay, so integral with respect to z, integral with respect to z. So h, which is what I was looking for, what's the h function, is just z cubed plus a, now I can say plus a constant. Now I can say that. And so I'm ready for my final version of f. Little f is this guy right here, x squared z plus xy squared plus some function h, which we turned out to determine was z cubed plus some constant. There's your potential function. So it is conservative vector field. It is. Not every vector field is conservative. So if you just threw some random vector field up on the board, the chances that you could do this and go backwards and get your little f are, it's not guaranteed, right? Do y'all believe that? That everything has to work out perfectly for conservative to happen.
I assume that you probably started with the scalar field to build this problem.
I don't remember where this problem came from. It was probably a textbook example or something. But yeah, you could always make your own problem by just generating a scalar function and taking the gradient.
Yeah.
So yeah, all right, I think that's good. I don't know if there's anything else I want to say about that. That's it for the section. Yeah, that seems short. Yeah, clap, cheering. All right, you done? You done? Let's just, I feel like this is worth an example here. Let's say I have the field, let's do a two-dimensional vector field. Let's go with x, y squared plus, x, y squared, and then here, let's make this one y minus x squared. All right, is that conservative? Why not? Yeah, I just threw something on the board. I could have made it work. Okay, what's the partial of p with respect to y? So I'm taking the partial of that with respect to y, 2xy. What's the partial of q with respect to x? What was that? Hold on. Keep going. We'll leave that locked. All right. Partial of q with respect to x? Negative 2x. These aren't the same. It is not conservative, right? Let's just try. I want us to see what would happen if we try to go backwards. All right, this right here if it was conservative, this would have to be the partial of little f with respect to x. That would have to be the partial of little f with respect to y, right? That's what would have to happen. So I'll start out with the first part. Let's go backwards. Little f, I'm taking the antiderivative of this with respect to x would be? One half x squared, y squared, plus, I could possibly have some y's in there, right? G of y? G of y. All right, now differentiate that real quick with respect to y. Differentiation of this with respect to y is x squared y plus whatever derivative of g is with respect to y, but we would need that to be equal to what's up there, y minus x squared, right? And there's nothing you're going to be able to do, because if you try and solve for this, nothing goes away, so you get partial of g with respect to y is y minus x squared y, right? So now what you're saying is that there's x's in here, right? But this said that g couldn't have x's, it just had y's in it. So you've got this contradiction that the way you defined this was that it had to be a function of y only. But this shows that it would have to have x's in it. So you're done at that point. All right. With that, you should be able to finish the mini exam. Yeah. For number 4, same type of work. I'm not sure which.
That's how we do number 4.
I don't remember what number 4 was, actually.
It was the one that you said we couldn't do until after.
I said you shouldn't do until after today. So I think, is that the one where I show you a picture of a curve and two, yeah? Yes? I think that's what it is, right?
X, Y, and Z.
Yeah.
So we would need to check the antiderivative most likely.
I'll just bring it up.
When I hear that, the news makes me think something's going to escalate.
What's going on? Are you worried about what we heard?
Oh, out there.
No, it's just,
No.
we're saying it's sad that we hear that and our immediate reaction is lock the door.
All right, so this problem, I tell you it's a conservative vector field, right?
Oh, find the potential function.
Find its potential function. So I am asking you to, is this what you're asking, right? Find the potential function. So yes, you are going to have to find the potential function.
How fun.
It looks worse than it is.
You say that.
It really does look worse than it
You
is.
say that, to be honest, because it looks really bad.
It does look bad, but it's not as bad as it looks.
People can go away.
Yeah. Yeah.
So that's the word backwards thing.
And then I ask you to find the work done where you're moving along this curve, the work done over that vector field when you're moving along this curve. And I give you this really nice curve, and I show you a picture of the curve as well. And the picture's actually really important.
Oh, it is?
Yeah. Well, it can be.
Well,
That picture can be really important.
oh, hey, wait a minute.
All right, that's all I'm saying about that. Let's move on.
Thank you.
Well, I'll just say it this way. There's an easy way through that problem. There's a hard way through that problem. So that's why I didn't want you to start on that last week, because now after today, there's easier ways to do things in certain scenarios. If you have conservative vector fields, I'll shut up.
Right. I meant about the advice, not the specific.
All right. Green's theorem. All right.
The one you said was like the miracle theorem?
Well, the Green's theorem is actually this is a two-dimensional version of a theorem. There's a three-dimensional, which I would argue is better than this one because it's the higher dimensional case. Good luck out there. What? I'm just saying. Oh, is he just going to check it out? We'll see. If you're not back in 5 minutes, right? Then we'll cancel class. All right, sorry about that. All right, Green's theorem. I meant it though, good luck. I mean, that's, yeah. What's up?
I have a question back. I was trying to ask it before we swapped over to this, but the fundamental theorem of line that extends to the 3D space as well, correct? Or no?
Yes. Yes. The fundamental theorem of line integrals says that if you're trying to evaluate the work over a field on some curve, right, that if the field is conservative, that means it has a potential function.
Correct. Which means
Then the value of the line integral is just the difference of the value of the scalar function evaluated at the two endpoints of the curve.
okay.
So if you can find the scalar function
Yeah.
and you know the two endpoints of the curve, it's pretty simple to do. Your alternative is to keep the field, plug all the pieces into it, dot that with the derivative of the curve, position function, and then go to town on an integration, which I don't suggest you do. All right, Green's theorem. This is a great theorem, all right? It miraculously gives us a connection between a line integral and a double integral, which seems like they should not be connected, but they are. And I just recently watched a really good video because, you know, math videos have gotten so much better over the years. There's a lot of money getting pumped into, you know, nice animations and things like that. And I forget who it was. I might find it and send you all the link. There's a real good visual representation of Green's theorem, but it requires, we are a little bit further in the book. So I won't send that to you until like a week before class ends. It's just a cool video. All right, so Green's theorem connects the line integral around a simple closed curve to the double integral of the region that it bounds. So let's just look at this picture. Let's say we have a curve, okay? C is the curve, and that it's closed. So it starts. All right, good? Is everyone freaking?
They don't know where he's at.
Did they say what? Was someone just yelling, mad, or?
So he was yelling, and apparently he went down.
All right, so you have a curve, right? It's closed, starts at a point, ends at a point. That should enclose a region, shouldn't it? That should enclose some region, which we're going to call D. So D is the inside of this, C is the curve going around it. And we're going to talk about something called positive orientation, which means that when you move along the curve, imagine this is you, this is your head, okay? We're looking down, right? And what you want is that as you walk along the curve, if I walk like this, the region should always be to my left, right, as I walk around. That would be positive orientation. If I reverse the arrows then, right, and I were walking, then the region would be to my right, wouldn't it? Like if I walk this way, the region would always be to my right. So that's positive orientation. This is called negative orientation. What's the theorem? The theorem says that if you want to find the value of this, now this is just a different notation of this. I started class with that notation, PQ, P dx, Q dy. I said that's the same thing as this, except this is the two-dimensional version of it. This is work, right? This is work. This is work over a closed curve. So if you want to calculate the work over a closed curve with positive orientation on that curve, it's just equal to the double integral over d, that's the region that it encloses, and then you do the partial of q with respect to x minus partial p with respect to y. You figure out what that is, and then you integrate that with respect to area. This symbol here with the circle around it, it's the first time we've ever seen this, that tells you that the curve C that we're integrating over is closed. It also implies that it's positive orientation. If you want it to be negative orientation, you have to draw it with an arrow on it where it goes clockwise. So positive orientation is counterclockwise, and then negative orientation is clockwise. So no arrow means positive orientation, counterclockwise. You have to put the arrow if you want to change the direction. Let's do an example. Oh, we only have 10 minutes? Yeah. All right, let's, 13 minutes. Let's evaluate this. We're going to do this two different ways. All right? I'm going to do it the easy way, the hard way first. That's before Green's theorem. Then I'm going to do it the easy way now that we have Green's theorem. So evaluate this, where C is the unit circle centered at the origin. So let's see if you remember how to do this. I'm going to take the unit circle centered at the origin, and I'm going to have to find parametric equations for this unit circle. X of t is cosine t, y of t is sine t, t is between 0 and 2 pi. That should draw me the unit circle, right? Then what I'm going to need to do is I'm going to need to plug in y and then the derivative of x. So I'm going to need the derivative of these. X prime t is negative sine t. And then y prime t, I'm going to need that as well. Here I go. This becomes the integral from 0 to 2 pi. And I'm going to do these one at a time. What's y for us? What's y? Sine t. So sine t times dx. What's dx for us? Careful, x negative sine t. Right? And then I'm going to do minus, and now I'm going to do this one. What's x? Cosine t. And then what's dy? Cosine t. All of that, dt. And this actually isn't that bad, right? It's 0 to pi. This is negative. Let's just pull a can we pull a negative out of the whole thing? Negative out of this, negative out of that, and we'll be left with sine squared t plus cosine squared t. dt, that's 1, right? So minus integral 0 to 2 pi of 1 dt. That's negative t evaluated from 0 to 2 pi. Yeah? Who was that? Oh, I didn't see. Okay, I was like, he looks a little different when he. Are these the tests?
Yes.
Yeah. Okay. What's the answer there? Negative 2 pi. Any questions on that? This is not using Green's theorem. We can use Green's theorem, though. And what tells us we can use Green's theorem is that this curve that we went around, did we draw that in that order? Like, did we go in that direction? If t starts at 0 and ends at 2 pi, we start here and then it goes around counterclockwise, right? Mm-hmm. So this c that we have that goes around is positive orientation. It's positive orientation, right? And it encloses a region, right? It encloses this region D, right? It encloses that region D. And so by Green's theorem, I don't have to do any of that. Green's theorem says I should be able to do this. this should be equal to the double integral over that region D of the, y'all want to see the formula again?
Yeah.
The partial of Q with respect to X minus the partial of P with respect to Y. This is P, that's Q, including the negative there. So what's the partial of Q with respect to X?
Zero. Wait, partial derivative.
Partial of, this is the Q. Q is this right here. Negative 1 is a derivative of that with respect to X. So negative 1. Okay, and then minus, look, this is the formula. That's Green's theorem. Minus 1. dA. Did y'all see where those came from? No questions? Sure? That's just negative 2, isn't it? That can come out. Watch this. This is the beautiful part. This is the beautiful part right here. Negative 2 times this. Go back and think about double integrals. It's been a while. But if you ever want to do the double integral over some region D of 1 dA, what is that really going to be giving you? The area of D, right? So isn't this just the area of D? And D is that circle. What's the area of this circle? Pi r squared. What's the radius? 1. Pi r squared would then be, what's the area? Pi. That's the same answer. What's wrong? You all right? It is weird. See how nice, and from here on out, if you ever get something like this, you don't have to go like do this double integral. If you did this double integral, you'd have to go to polar coordinates and you'd have to do all that stuff. But we all know what the area of that circle is. So we're going to use the fact that this double integral represents the area of that. And it's going to happen more times than you might imagine it happens, things like this. So we'll do more. I think this probably, oh yeah, let's do this. This is super. This one's so easy. We can do this in the 7 minutes we have. Look at this disaster. Look at this disaster of a line integral. Now this is just a problem to kind of like illustrate, like you don't want to be doing things with blinders on, right? This is a line integral. Holy crap, it looks terrible. This is your P. This is your Q. And then we're doing this over this circle. We're going positive orientation, has a radius of 3. Think about how bad this would be to not use Green's theorem on, right? You'd have to find the parametric equations for the circle and then start plugging all those pieces in here. It'd be so bad. But this encloses a region D, right? And so this should just become, because that's a closed curve, the double integral over D, partial of Q with respect to X. What's the partial of this with respect to X? 7. Minus partial of that with respect to Y? 3. dA. That's a constant. 4. Pop it out. 4 times a double integral over D of 1 dA. Right? And that double integral over D of 1 dA is just the area of the region D, which is pi r squared, and the radius here is 3. So 9 pi is the area of that. So this should be 4 times 9 pi, which is 36 pi. See, if you know what you're supposed to be doing there, that problem is trivial almost, right? But if you don't know what you're supposed to be doing, you could go down this disastrous rabbit hole of trying to actually like find the parametric equations for this, right? So Green's theorem, what are some of the things that we would be looking for that would tip us off Green's theorem? Closed curve, right? If your path is closed, then be thinking Green's. If it's not closed, then be hoping for fundamental theorem of line integrals, which means you need a potential function, right? And if you don't have a potential function, it's not closed, then you got to do it the hard way, the grind it out way. Okay, let's call it a day. Yeah?
All right.
Yep. Okay. All right, everybody. I may or may not see you on Wednesday.
Good Lord, man.